Okay, we're going to talk about sets today. So, what's a set? And the answer is a set is just a collection of objects or elements. So, a set is just a collection of stuff. Now, we've got some common sets. The first common set is called the universal set, and we denote it by a big U. Get it? U for universal. What is it? It's the set of all elements of interest. So the universal set contains everything. Another common set is the set called the null set, and it's the set that contains nothing. Shorthand for the null set is just a zero with a slash through it. Computer scientists sometimes like to use this symbol to denote zero, but for a mathematician it means the null set. So how can I write the null set? Well, anytime I want to indicate a set, first off, I write ellipses, rather braces, curly braces right here. So anytime you see curly braces, it means the set of. So this is the set of, and then I write any elements inside here. Well, there's nothing there, so that's the set of nothing, which, by the way, is the null set. Word of warning, this mixing of those two symbols is not the null set, because this set has something in it, namely the null set. So this is not the null set, whereas this or this is. All right, there's lots of ways I can list a set. One is by a rule, and we use what's called set builder notation. So this means the set of X is a dummy variable. It represents anything in the set. And then if I have a slash like that or a colon, either one, you can replace it with the phrase such that. So this is the set of X such that, and then I give a rule. In this case, let's say X is a natural number. So there's another way I can just denote the natural numbers. What's even another way? Well, I could list enough elements to where you figure out what the pattern is. And then I could write the ellipses to tell you to keep on going. So if I write the set 1, 2, 3, 4, 5, you could figure the next element is 6. 7, then, and you keep on going, that's also the natural numbers. And by the way, I'll remind you that we also have a shorthand for the natural numbers, just a big N with a double bar. Okay, with respect to sets, there are a couple of things that are important. For a set, repetition makes no difference. I don't care if you repeat an element. You haven't changed the set. And order doesn't matter. So I don't care what order you list the elements in, you haven't changed the set. So for sets, repetition and order do not matter. Now, we're going to be talking about sequences soon. And for a sequence, repetition and order does make a difference, but not for sets. Okay, a little more notation. If I want to say X is an element of A, in other words, X is inside A, I write X epsilon A. So this epsilon can be read element of. X element of A. By the same token, if I want to say X is not in A, equivalently X is not an element of A, I would write X epsilon with a slash A. Get it? Okay, if you think about symbolic logic, the basic building block of symbolic logic are prepositions. And what do we do with propositions? We combine them using binary operations. Well, the same thing is true about sets. So the first binary operation I want to talk about is intersection. And intersection is denoted by this upside down U, kind of looks like an N. So N for intersection. And what does it mean? Well, A intersect B is the set of X such that X is an element of A and X is an element of B. Now remember, that's and. We use that when we're in symbolic logic. When is that statement true? They both have to be true. So what is in the intersection? And the answer is the intersection contains all the elements they have in common. Hence, if I look at this example where A is 1, 2, 3, 4, 5, B is 2, 4, 6, 8, 10. If I want A intersect B, I look at what they have in common, and it turns out to be the set 2, 4. Okay, I'd like to just remind you that's also the set 2, 2, 4. Why? Because repetition doesn't matter. It's also the set 4, 2. Why? Because order doesn't matter for sets. As a point of clarification, two sets are the same or equal when they have the same elements. So if I want to check to see if two sets are equal, I simply make sure that they both have the same elements. The next binary operation I want to talk about is union. What does it mean for two sets to be unioned? Well, A union B is defined as the set of X such that X is in A or, that's the disjunction, X is in B. Now, what does it take for the disjunction to be true? And the answer is, I just need one of them to be true. So, A union B consists of all the elements that are either in A or in B. Right? So if I want to take the set 1, 2, 3, 4, 5 and union it with the set 2, 4, 6, 8, 10, then what do I have to do? Well, I have to put everything that's in A, it's in there, 1, 2, 3, 4, 5. And then everything that's in B, I have to put in there as well. But I already have 2 and 4, so I just really need to add 6, 8, 10. Hence, A union B in this case is 1, 2, 3, 4, 5, 6, 8, and 10. The next binary operation is called set subtraction. It's denoted by either a dash or a slanted line and is read A not B. Okay, so you see this, you read it A not B. What is A not B? And the answer is, it's anything that's in A but not in B. Make sense? So what you do is you start with A and then you throw out anything that's in B. Okay, so in our previous example again, here we have A not B. So I would take the set 1, 2, 3, 4, 5. I would throw out anything that's in the set 2, 4, 6, 8, 10. And so I start with this set and I throw out anything in the second set. Well, all I have to throw out is what? 2 and 4. Hence, A not B in this case is the set 1, 3, 5. By the same token, if I wanted to look at B not A, I would start with the set B, 2, 4, 6, 8, 10. And I would throw out anything that was in this set. But the only thing that's in this set that I see over there is 2 and 4. So I'd throw those out and I'd end up with the set 6, 8, 10. Okay, so that is union, intersection, and set subtraction. And on the next video, I'll pick it up